right, good. I'll I'll introduce you for a few minutes.
Okay.
And then you can start.
Okay.
And go on for until 12:50.
Okay.
You can still have lunch during the time if you want.
Okay.
And then we'll have question and answers. So, okay. So, good afternoon. Thank you for coming. People in person here. I know you have to drive in this rain and then park and come in. It's I hope that is worth it. At the end of the hour, you will know that. Please do have these lunch boxes. There are a few more left. And thanks for coming. That's really valuable for this. I am from IEEE Controls or Computational Intelligence Society chapter that is part of IEEE Schenectady Section. I also have a day job. I work at Path Science. It's a digital pathology company specializing in medical AI. So I have invited Dr. Chang. He's our collaborator as well through our company. And I got to know his work a little bit. And then we found, oh, this is very much in agreement with what we wanted to do in future. So we set up a collaboration and his student works with us. And that's amazing. And I invited Dr. Chang to come here and give a talk. He is from UAlbany. He's a professor in the Department of Computer Science. And it is affiliated to College of Nanoscience and Technology, Nanotechnology, Science and Engineering. Interestingly, he is very dynamic. He has been in this computational or computer vision area for quite some time. He's published so many papers, 190 papers, being so young, getting all of those in peer-reviewed journals is not easy. And also he has 7 US patents. I hope that's making money. Yeah. So he is involved in many conferences. He is program chair as well as general chair for some conferences. I think that was in Buffalo. Yeah. So very active in this field. So he has been doing AI. Agentic AI is the most recent and new one. So I thought it's a good idea to have him present and enlighten our audience. For those who are joining virtually, please note that we will have this talk until 12:50. After that, there will be a question and answer session. I have 5 questions for those who are here for PDH credits, and we need it will be open to the audience, so they can just answer those questions, and that will satisfy the IEEE requirement. Okay, thank you. Floor is yours now.
Okay, thank you. Okay, all right. Yeah, I'm thrilled to give a talk here. Can everybody? And is this good? Should I use the microphone? Is it good? Okay. All right. Yeah. So, let's see. Next slide. Come on. Okay. Yeah, this is like a quick of like some bio of myself that can skip. Okay. So today I mostly divide my talk into like 3 parts, right? So first is the overview of the history of AI all the way from the old days all the way to the agentic AI that we, you see hear all these buzzwords of the, the deep learning foundation models, the LLM, large language models, the agentic AI, and then next, right, the trustworthy part, right? So the second part, I will try to convince you why this trustworthy AI is next, like a research direction and topics. It goes hand in hand with this agentic AI. When we have these powerful agents, this AI agent that can do many things, then the trustworthiness will be the key in many aspects. Later on, I would like to talk about many aspects. Each of the aspects will be a new research, ongoing research direction. For example, the fairness, the security, so different aspects, reliability, different aspects of trustworthy AI. And the third part, if the time allows, I will go through some of my published papers. That would be something like 1 slide per paper to show my recent work under this umbrella of agentic and trustworthy AI. Okay, so that's the overview. That my bio, I was published. I can quickly jump. Okay, so so this is like introductory slides to that I use over the years. I mean, from the old days, we at some point, right? At some point, all this buzzword of AI was like everywhere. It like revolutionized everything I'm doing. So when I make this slide, I believe I was in GE research 10 years ago, and then they have a brainstorm section talking about, maybe AI will be the next buzzword. But at GE, we do this all the time. So a few years back, 2016, 14, we talked about, say, robotics, maybe the next buzzwords. And earlier we talked about, say, Internet of Things might be the buzzword, right? So every year we sort of hear about it. But this agentic AI, at that time, there's no natural agentic AI. It's just like like deep learning was booming, and then we see these buzzwords, and then at that time we don't realize it's like a revolution that's still continuing after 10 years, still ongoing, right? So I sort of put into some buzzwords you can see, right? So when the .com has a problem vaporized, the 2003, right? So that's the time that people talk about big data, right? So all of these are the driving forces that leads to the booming of this AI things that we are hearing about today. And then it's not just the technical improvements; it's affecting all kinds of education, like transportation, governance, different aspects of our everyday life, right? So the driving force, like we must have data, we must have computational power, no matter it's GPU on the cloud or the edge devices, and we must have algorithms, right? So the deep learning, that's the algorithmic improvement. And then you see as the thing goes on, right? So the foundation models is like shifting the paradigm, right? So it's not just designing deeper and deeper neural network. It's something like the model can be trained to do many tasks. So to somehow, going through there's a breakthrough that these models can now understand common sense, right? This foundation model, like a GPT, like AI agent we are using every day, right? It has a lot of customization, but it can understand a lot of common sense, right? Later on, I'll try to elaborate why this is like an important thing, right? If you do not have that, we cannot have this breakthrough, right? So when we talk about these trends, we should see what's the driving force. Like we are talking about exponential growth, right? So like a Moore's law, right? So this is the hardware aspect of what I'm talking about, right? So we must have data, we must have computational power, the hardware, right? And then we must have algorithms, these three, right? So when we look at the Moore's law, right? So this is a slide from Intel, right? You see most of the blue dots are the breakthrough from the CPU, and later on, the green or yellow dots are driven by the NVIDIA GPUs, right? And then more and more on-device ASIC kind of computation, right? So it's getting harder and harder to push the limit when we try to talk about this exponential growth, right? So, and then like again, history, right? So yeah, some people say we are at the industrial revolution 5.0. Some people say 4.0 because people can combine 3 and 4 together to call them. So there's a revolution on say mechanics, revolution on the electric power, the revolution on computers, and then now the next is the AI. Right, and then for AI, there is also not just growing smooth, right? So we see this the boom and the winter of AI, right? So and the history, right? So the expert systems was up, the first boom, and then I would say data-driven learning, small vector machine, that kind of thing was the second boom, and then now the deep learning. Right, so this is one of my the slides I try to generate using ChatGPT, right? So I try to make an analogy that AI is right at its booming its Wright brothers era, because think about this analogy, right? So how does airplane fly by aerodynamics, right? But when you take this technology, right? So the analogy is the deep neural networks and then the cloud computing, that kind of thing on the right, right? So these are the the driving force, the engineering thing that makes this agent think and then infer and work, right? So we must have some kind of infrastructure that the company can build it, make this into products, right? So you start to see that, the companies like OpenAI are making money, right? So making these systems to all the way that, today when we want to when I want to fly to anywhere, I can just buy a ticket and I don't need to worry about, if what will the plane crash is, right? So I won't be worry about, this kind of, the governance of things. So when we are talking about the trustworthy AI, we are on the upper right corner, right? So the whole industry will take, I think, 30 to 50 years to evolve such that, the AI technology we are talking about can be evolved into something that you can use every day. I mean, we actually start to use it every day, but you are not trusting so much, right? Because we are still in the process of digesting this kind of phase evolution in the phase pace. Okay. So yeah, agentic AI. I would say the driving force of this is all start from these large language models. This is basically the thinking power that you can use it to to apply to process many all kinds of the information you want to process. Okay, so this is the core capability that's based on this transformers that you can process information. Okay, so once you have this capability, so this is basically abstraction of the task and the knowledge into a language tokens, right? And then the AI agent is nothing more than just engineering of this LLM such that you can do many things, right? So the AI agent can iterate on the planning and reasoning, the capability of it, right? Based on the LLM inference capability, right? So based on that, for the AI agent, you can build the infrastructure and make these AI systems, agentic systems that can run this in a large scale and then build a whole infrastructure. Okay, so think about what's the driving force of this LLM, that we all know today, right? So it's based on this transformer model, right? So, this 2017, right? So attention is all you need paper talk about this transformer, right? So for an active researcher in this field, you must have been reading this seeing this paper so many times, right? So attention is all you need paper, right? So I want to point out an important idea here. So why is this transformer working so well? I mean, you must have been seeing this in when you read this paper or blogs or doing your research, you find out people tell you that the transformer can replace a recurrent neural network, and transformer can replace and outperform a convolutional neural network. Right. So basically, everything is and in this mechanism and this attention mechanism transformer is doing is basically doing the whole magic. Right. So I'm trying to explain the most important idea. So in my view, the most important idea is this: the keyword, transduction. Right. So what? Come on. So what is a transduction? Right. So the first sentence of this paper, right? The dominant sequence transduction model based on blah, right? Based on what? Based on the recurrent neural network and a convolutional neural network. Right. So that means this first sentence tells us the recurrent neural network and the convolutional neural network are designed to do this sequence transduction. So the question, what is transduction? Or in the other question, similar, what are the transducers? Right? If you know what the transducer, then you know what this transformer is doing. Okay. So as an engineer, and when I read this, I'm pretty confused. Maybe my English not good enough. But what is transduction, right? Okay, let me tell you, right? So a transduction is a process of transforming one kind of sequential signal into another sequence, right? So these buzzwords also point to this 2014 paper called sequence-to-sequence learning. Okay, so sequence learning means, you have one sequence of signals. This model can digest or understand and map and transform to another sequence. So what are the examples of transducers that you can think about? Right, for example, this is everywhere, right? So for example, a microphone is a transducer. It takes the sound wave and then convert into electrical signals, right? So your ear is a transducer, right? Your eyes is transducer because you see, you take these lights, RGB lights, convert into the signal, some signal you can understand, right? So the moment you listen to me talking, your brain is a multifunctional transducer, right? Because you see my, visually you see me, you hear my talking, you understand this English, you translate and you understand what I'm doing. When I'm doing my body gesture, you also understand this body language, right? So the transformer, why is it so powerful? Because it can learn this kind of a transduction process. Okay, so once you see this, then this is just I use a GPT to generate this slide for me to explain, right? So once you see if transformer is good to do this, then for any problem you have, what do? You convert them into some sequence to sequence conversion learning problem. Then you apply transformer. Then you collect lots of data and you train it. And you can solve the problem, right? So this is the sequence, right? So you convert your problem into some kind of the tokenization. You make them into tokens, right? Speech, text, or the images. Then you apply transformer. So the transformer is doing the magic of the attention mechanism, right? The self-attention, the cross-attention. So the encoder will be the one self-attention, right? The cross-attention will do the translation by the mapping. And then the decoder is another self-attention that produce output sequence, right? And then you can detokenize and get your output, right? So this could be image, text, voice. The output will be the other set of the other domain, right? Translated image, translate English, Chinese, right? So all these kind of digestions, right? So all the things is done on this framework. And then the important thing for the large language model is that if you train it with internet scale of data, the model can not just do one text. It can do many texts. And the thing is, if you train them with this large scale of data, it will perform better than just that one single text. Okay, so the analogy is, if the transformer can translate, say, Chinese to English, English to French, and French to Chinese again, like instead of training 3 models, you should just dump all of them to it, and then the one single model can do all the 3 jobs better. Because of what? Because you can, that way you have larger data. Okay, so that's why this when you see this picture, right, this figure in this transformer like a paper, right, it's hard to understand what's going on, right? This encoders, the cross attention is just this line, right, from left to right, and then the decoder on the right, right? So all this is like engineering designs that I think, if you understand what the transducer is doing, then the question here is like, what kind of engineering design can do this better? Then the answer is the attention mechanism, right? The query key and value, the 2KB networks that can design to do self-supervised learning. That means you can just, like I said, you provide a sufficiently large enough data, and then you learn the attention mechanism to learn the mappings. And then the mappings will just say, self-supervised learning means you don't need to label it, right? So you can just learn the attention and so on. Then it's effective. Okay. So, with that, we have these transformer models that can, like I said, right? So basically, it operates mostly on this natural language processing. And then it extends to vision language models, and it extends to multimodalities, right? And then now the latest frontier is it extends to the thing called the word models, right? Vision language action models, right? For example, right? So this sequence-to-sequence learning is very powerful. The vision language action model means people do this for this robot arm controls, right? So I give you a picture of this robot arm moving things. I give you the language, like the instruction, take this box, put it in another place, right? And then the action model is the motor control. So this VLA model can directly learn this kind of thing of how do I control to get the goal, right? So you basically apply this mechanism, you change the token, right? So the token you want, it could be like language tokens or visual tokens or the audio tokens or action tokens. Then, from the generated model, you generate the action token. Basically, you generate actions that can work, right? So that's why we are moving toward these world models, because we want the models now to perceive, to learn, how this world can be operating, right? So based on physics, okay. So that's one of the things that is moving on, okay. So yeah, this slide, yeah, this is just the open cloud. I think it's quite popular a few months ago. Now it's not so popular because there are many other tools coming out. But you see the trend is like in this open source community, we are moving from the prompt engineering, like how do I ask my question, into the design of the prompt. So if I ask the question in a better way, I get a better feedback, right? So you transform that into the thing called harness engineering, right? So this is like, so the word harness means you are riding a horse, right? So the AI is the horse. You are designing this harness framework like OpenCloud. You are designing the framework such that the agent will prompt itself, right? So the single loop engineering is basically you do the harness, you give a test, and then the agent will prompt itself to write code and to debug the code and to test the code, and then based on the feedback, it will prompt itself again, right? So once you are at here, your agent can do a lot of automatic things, right? You can just give the command, and hopefully the agent will correct itself. Multiple agents could debate, right? So one agent can force sub-agents to do things, and then they can debate, and then they can, like I said, write code and then debug, and then, finally they convert to something like good as an output, right? So we are, I think we are at this very active field of loop engineering. I think many of my research, my PhD students are sort of using this to, I think if you do this right, if you set up your problem statement right, you can almost get answer in very few, 3-4 days. You get a good draft, right? So it's moving so fast. Okay, so this is one of the slides I like. So this Professor Liang, he is also a senior director of MediaTek. So this is a company in Taiwan who does something like Qualcomm. It's just like a Qualcomm chip designer. Right? So he has this single author paper talking about this computer architecture of AI, right? So this is an analogy to our TCP/IP 7-layer architecture, right? So the bottom 3 layers is like the physical layer, the GPU, right? So the design, and then it's the software, right? The neural network, right? The transformer or and the network model here, right? And then the layer 4 is like how do you set up the context, right? Something like the domain knowledge, right? So you use the transformer, you fine tune on which data set, video, audio, or what, right? On top of the context, once the agent knows about this knowledge context, the agent layer is basically like what kind of agent you're using, OpenAI, RAW, or the others, right? So orchestra layer is the layer that an agent can control and sub-agents and communicate with sub-agents. And then the application layer is basically talk to us as human beings, right? So I think it's a pretty good architecture. That the analogy is like, the bottom 3 layers is to build these basic organs that an agent is composed of, right? These are the components that you need to make things work, right? So like pre-trained models, like which version of Llama, that kind of models are at here. Okay, and then the context there is like I said, the different domains, right? So this is like like which company or who controls data and owns that territory. For example, the Amazon has this transaction data set, like Meta, Facebook has the social network data, like Google has the search and the YouTube has the video data, right? So who holds the most data has the most powerful generation capability, right? If you want to generate a video, you will probably think, Gemini is the best. Right? If you want to write code, probably Cloud is the best. If you want to plan your trip, maybe OpenAI is the best. Right? Because they own this territory, so they have the context. Okay, so and then like I said, the agent layer is basically the AI agent that takes this context and do some integration for the harness engineering, the loop engineering, such that the agent can know how to do planning and how to solve the task. Okay, so that's the task, the agent that can do one task, and the orchestra layer is like agent and sub-agents, and then maybe so think about here, right? So you will not always want the best agent to do everything for you because there's too much waste of energy and money. Right? You want some agent that's good for, say, doing, say, translation. Some agent is good for coding. Some other agent is good for summarizing and generate PowerPoint for you. Right? So each of these the agent has their own capabilities, and some of them will run on your cell phone. Some of them will run on cloud. Right? So data privacy and efficiency will be the key in this design. Okay, and finally, the agent that it encapsulates the physical, interface. Okay, yeah. So yeah, I think this is just like another way to talk about where we are. We are sort of at this, from the LLM, right? So we do a pre-training. How do we make this LLM better? We do post-training. This is called, the instruction fine-tuning. So you take the LLM and tell it how to decompose problem and planning. Okay, and then we have this test time. This test time is like the LoRa, LoRa or the RAG, retrieval augmented generation. Something like if your LLM does not know about what happened yesterday, like there's a flood in Albany yesterday, you ask GPT, what is the flooding, how does the agent still know? Because you can do some kind of query, right, internet search, and then summarize. Like, so that's the text time compute. Like, so this we are sort of at here, that we have this AI agent that can do many multiple things, and we are looking forward that when we talk about this physical AI and the world models, we are imagining each of those there is an agent, some kind of LLM that will link to the physical body, something like the LLM has. And then the agent has to have a body such that we can do think something like a reinforcement learning, right? And try and test and then get rewards. Right, that way you can self-improve. Okay, so that's the role model. Like I said, the role model of this. We are moving from this software kind of agentic AI into the physical world agents. Right, so this is like a territory that's completely new, right? So what I mean is that when you want your agent to learn this about physical worlds, you basically have to collect new set of data, right? So which company or who owns the most data will be the most successful, right? So take an example, Tesla, the autonomous driving cars, right? So you need the key data to make it work the best, right? So for drones and for the cars, I think data. We still go back to the data again, right? Who owns the territory will have the best model. Okay, so it's like a beautiful road ahead, but it's not perfect, right? So what are the the obstacles, right? So we have this depth, right? So this is like the difficult we have, right? On the bottom level, we have this prompt depth. That means how do I design a prompt that asks the right question such that you can reduce this hallucination? Okay, we do not have this context then that something like the thing is that you do not know if you know the answer, you know how to ask. But you get that problem. Sometimes I just don't know how to ask the right question to get to the answer. because you have huge data, right? Usually the case is that there is an answer somewhere. You just, I don't know a way to get it. Okay, so let's contact that. And also, the second way to look at this is that, the transformer model has this, n square quadratic complexity, right? So you must have this experience. You talk to GPT and again and again. The longer it becomes slower and slower, right? Because the context window, the memory, is getting larger and larger, and then at some point, this AI agent cannot do it anymore. You have to compress. You have to compress your memory, right? So that's the context there. Right, so which prompt that's more close to what you just add is more important than your memory, your history. Okay, but this is like a drawback, right? So that's why they right. The intent there is like it's like a high level, right? How do you want to use this LLM agent, and then at the top it's the governance, right? So is the AI agent doing the right thing or not? Okay, so we are still. I also try to use GPT to generate, but I don't like this picture. It's not doing the right. I mean, the point here is, we are going toward this reinforcement learning, right? So we are trying to build an agent that can like we need the life, right? We need this animal or human capability that this agent can live and perceive the world and then self-evolve. Okay, that's the goal. But it's really hard, right? Because so if you look into this reinforcement learning algorithm, how does it work? Reinforcement learning improves based on try and error, right? So the thing is the thing called regret, right? So your agent, before your agent do something stupid, does not know if it's good or bad, unless you have some kind of knowledge to tell this record that you cannot do it, otherwise you will die, right? I mean, this kind of the skill to achieve this zero grade intelligence is still far away from what we have. Okay, I mean the agentic AI today cannot do this. Okay, so this is one of our goal, right? So how are we far from people call this AGI, right? Agentic general intelligence. People say there's something called better one, super intelligence, and some people the first term is called artificial ultimate intelligence. That's like a god, right? AUI, ASI, and AGI, like 3 level. I think we are sort of close to do AGI, right? So if you, look today, right? If you say who is the best, like a Python code writer, I think AI is the best, right? So we are sort of achieving AGI at some domain. But for planning and for, say, solving the math equations, I don't know, sort of API is sort of that coming, but not so in every front. Okay, so these are some like famous quotes, and are we close? I don't know, but I think we are still like 10, 20 years far away from need to worry about this. Okay, so that also brings to my second topic, on trustworthy AI. Okay, as long as your agent is so powerful in doing things, the next thing you want to worry is that can I trust this AI agent, right? So let's go back to how does this agent work? Like again, right? So I just talked about this transformer architecture, right? So, but we take a step back. So the transformer is based on this end-to-end deep neural network, right? End-to-end data-driven learning, right? So what is machine learning, right? So we use 3 kind of big domains of machine learning, like classification problems and regression problems, and then generative problems, right? These are the 3 machine learning tasks. They are all data-driven. Okay, and then there are so many improvements. I call them like X learning, something like transfer learning, right? Domain interpretation, few-shot learning, right? Noise-level learning, federative learning. There are just so many kinds of learning algorithms that do this kind of thing and improve on different aspects. But their basis is still data-driven learning, right? So conceptually, when we talk about my wish of a trustworthy AI, they are not trustworthy, right? Because based on this data-driven learning, so when can this model work? The model is a black box, right? It can only work when your training domain and your test domain are almost the same. And it can only work when the algorithm you pick is very good, right? So you pick transformer, you pick CNN or whatever, right? You pick a good model, you have sufficient amount of data, and you have good enough GPU to train, and you have a good ratio and to tune up what's running, and it works very well. Then it works. Otherwise, it doesn't work, right? So when we talk about trustworthy AI, the thing is not trustworthy. Right, so we are, like I said, we are in a long roadmap of improving its trustworthy AI. And if you are a grad student, you most care about this, taking the data, train a model, and then do it. Like you can graduate, get your PhD, get your paper published, like that. But in reality, this is a cycle, right? So in the industry, we have to deploy a model, we have to validate and then test, and then based on the feedback, we have to do this develop ops. It's an infinity cycle, right? So for each of the steps, we try to use AI or rely on it. There is like a trustworthiness issue. So this slide I try to improve over the years, right? So these are many aspects of this trustworthiness. So trustworthy machine learning. Okay, so each of these bullets. Let me very quickly go through it, right? So efficiency of this model, right? So can I train a model with less amount of data? Can I use a smaller model for model efficiency? Right. The second bullet, the robustness, right? So when I test my model on a different domain, does it work? Run on different device, does it work? Or I do a different compilation, does it work? Like robustness, right? The fairness. Right, if I make this model work to this group of people, right, does it work for the other group? So fairness is a big issue, right? So it could be the token fairness, right? So who can use it more, right? It could be data fairness, it could be model fairness, right? So there are many aspects of that, like financial fairness, right? So if OpenAI is earning that much money, right? So in its training, using all of our data to train, right? Do we get some credit of it? So far, no, right? So fairness is an issue, right? Privacy is an issue, right? So because we do data-driven learning, so the more data, the model will work better, right? But as a user perspective, we want to go the other way. We hope that that it's better that the model does not use any of my data, right? Right. So privacy. How do you balance between the two, right? So you want to get sort of like high quality data, but also protecting users' privacy. Right, you must do a lot of transfer learning in order to do that. Okay, so security is like a privacy, but the difference is that the privacy. For example, I want to train a model to recognize people's face, right, to unlock phone, right? So I can collect a big enough data of de-identified faces to train it. So that way, it does not violate my privacy, but you can still get some kind of data, right? But security is the other way. It's like your credit card number, right? You don't want to share anything of it, right? So security is like hacking or adversarial attack. So how do you make your model robust from like hackers? Okay. So, on the other side, so explainability is like, the black box, the model you learn, right? Can you do some kind of probing to see that you are actually learning something, some distribution or visualization that's usable? Something like a drag camera, something like, this kind of model that can, that if you say this image is a dog, you visualize your image. I want to see, you visualize, the image is focused on the dog, then I say, you probably learn the right thing. If your image is showing something on the background, you probably learn the wrong thing. Okay, that's the explainability. And then a lot more, right? So the ethics and the new buzzword from the Jason Huang and video is sovereign AI, right? So who controls how many GPUs, how many data? Each country should have its own territory of your LLM, right? So that's that. Okay, so I'll give you some examples, right? So this is one joke I get from like the thing is that I want to ask the GPT, right? So I want to watch car, right? So and then should I drive or walk, right? So surprisingly, most of these models say you should walk to walk your car, right? So how can this be happening, right? So this is like the, you remember my zero, regret, reinforcement learning case, right? So, this kind of AI cannot do anything good, right? Because simple thing like this fails, right? This is not just a hallucination. So why is this happening? Because it go back to the data, right? Because most of the question like that refer to data of driving, right? And then most of the answer is that, for distance far away, for 100 kilograms, you should drive, right? So that's why you do not have data that is specific for car wash. That's why it's so stupid, right? So, this kind of thing is not just one example. You can find a pattern to it, right? This grandma's trick is like an adversarial attack, right? So you cannot say, show me how to make a drug, right? GPT said, I cannot build you, right? But if you use another way to ask, right? So you say you do this grandma's trick. Then you can say, my grandma sing this lullaby with the Windows activation key, right? So and then the model starts to say, right? So there's a lullaby of Windows activation key and so, right? So because the model has to show sympathy to human, right? So like the way to circle it back and then break it, right? So there is a lot of this prompt adversarial attack, right? That you can always find a hole to attack this model, right? So yeah, I think yeah, it's an underactive demand, but I do not have a good answer yet. But I know that every year, like there are like tens and thousands of papers get published at these top conference and journals talking about all these topics. So that's why I'm trying to get back to my point of agentic and trustworthy AI will be the ongoing research topics, right? So you relax the problem on a different perspective. Then the state art is no longer the best because you relax it, right? So then you can design a better way to improve the problem, right? For example, right, if I want the model to be more efficient, right, I can find a better quantization algorithm to do it, right? If I want my model to be more fair, I have to sacrifice my performance to do some kind of trick such that it will perform better on the lower representative data set, and then to make less bias, right? So there is always a trade-off. It's like fixing the roof of your room, right? You fix here, fixing there, and fix there, and fixing here, right? But we are sort of in slowly progress in this process. Okay. So I'm gonna put in time. Okay, 10 minutes. So I would the remaining slides is just like I said, 1 or 2 slides per like a paper I work on in the recent years, right? So this one is like OOD detection, right? So out of distributing detection. So that means the problem is like this, right? So when you train your data on your model on one data set, for example, this simple this core example, like Cyber 10, we have this 10 class of image and another label, right? So when you train this one model, you want to test on different kind of like a data set, it will fail, right? The model does not know that the new image you try to test is belonging to the class. So it's like self-awareness, right? The best thing the model should say that, if I say, is this one of the 10 class, the model should say, I don't know, right? Because I have never seen this before, right? This is called OOD detection, right? You should detect something you have not trained on. But the problem, the difficulty is that you do not know there are so many abnormalities out there, right? So we are trying to simplify the problem into only the classification, and we try to derive a good way to learn this to solve this problem, right? So then, our solution is sort of like learning and embedding, right? Something like you project all your data, you learn this embedding process, you take your training data, you do your projection such that the within class variation and between class variation are optimized. That way, when you are asking something new, a new image I ask, you project into that hyper severe the representation, and if it's outside the board, then you say this is something I've never thought. Right, that is called a hypersevere projection. Right, so in our paper, we also do with hyperbolic projection, because a hyperbolic representation is sort of naturally doing this. You can learn this branching structure naturally, hyperbolic. So basically, we combine the two and we do the tuning, and we get a good result. Okay, so that's this paper. And for this topic of addressing fairness and bias, okay, and media bias, I'll show you like two papers. So this paper is on addressing this fairness of image generation. So what we found is that you can give a prompt, like give me generate like a doctor or a nurse or whatever. Then what we found out is that there's a bias, right? So if you do not do anything, right, mostly the doctor will be male, right? Nurse will be female. Then people say they're not good, right? So the better thing is that you should have the equal sex on all of the jobs you are generating, right? So that's the goal to be fair. Okay. Then we found out that if you do some kind of thing, so that's no problem. What we found is that if you do some kind of decoration, like this is kind of like a doctor wearing a pink hat or a pink shirt, something less in your training set, then you do that kind of thing, it doesn't work. Because again, you go back to the scarcity of data again. Right, so here we find out that this is a common thing, right? So you add this kind of decoration to say something like strange color of hair, dress, something, then the model will not do good, right? So the fairness fix is now there. So what we did is we try to learn this embedding. We try to learn this kind of some kind of like a voting, right? You can know which token has this bias adhesive to it, right? Some kind of distribution that from your collected data that you find it's pretty uneven, it's unfair, very biased data set. Then we try to learn to decouple it. I'll skip all the details. So what we found out is that you can do this, and then we can get this some kind of like interesting observation that, for example, right, a photo of a assistant wearing a pink hat, right? You can generate this. Then you can start to take some of the token out. You say that, say for example, right, pink is very adhesive to email, so we take that out, and you generate again. Okay, so you can do this kind of thing. Learn the projection and take the biased token out to make it unbiased and put it in, right? I can say it that way. And at some point, you can really address bias. But if you take it too much, like if I say, all of these are very biased, I take all of them out, you will generate something that you fail, basically. Okay, so that means that you can fix bias to some point, by this kind of trick, but there is a limit. It still go back to the limitation of the data set you will have. Okay, I have to go pretty fast, otherwise I cannot finish all my slides. Okay, for media bias, this is like there is a data set of this kind of the news articles, right? And then if you ask GPT to say, is this article biased or not, you will sort of get a 60% accuracy, right? Because it's a hard problem, right? So what we found is that you can doing something like a chain of thought. You can something to do this. You can ask it's a classic attribute, right? So is there any body language? Is there any opinion or injecting opinion? For each of these, you can individually ask by carefully design a prompt. And then you carefully design a prompt such that the LLM you are doing before will tell you, if it's fine or not with some confidence score. Right? Then you take this confidence, each of these attributes, and you verify the confidence, and you do smart fusion, then you will do a better job. Right? So basically, a lot of details. We have to smartly design these three scoring ways to combine, and you can do it better. Okay, so this is like a train of thought. Okay, the next one is this. I do a lot of computer vision, right? So all these three papers is on this the problem called the moment retrieval. Right, the problem is, let me jump to the problem. The problem is like this. Sorry. given a video, right, and then given a prompt, like query, like a man wearing a sunglasses in the interview next to the bed, right, in the video, given that, then the model has to predict, from which frame to which frame, is that event, right? This is called the moment retrieval problem. So how does this do? I think the best way these days is still you use large vision language models to do it. You fine-tune a large vision language model on this kind of data set, and then you fine-tune it with a large set that with a set of this query and the video and ground truth, and you fine-tune basically you get your results. Okay, so that's what the problem is. And what we found is that if you want to do a better job, you have to do a good job on token pruning. So that means basically that the key is removing the non-representative token to make the problem smaller. And that way, when you run this attention mechanism and square, you will perform better. Okay, so that's basically what I'm doing here on this token efficiency. Skip all the details. And then this next paper we work on is in addition, we also consider audio. Right? This audio could be people talking, it could be some background noise, like people opening the door, making sound. But they are all like represented with audio tokens. And then the solution is sort of still similar. It's like what we found is that for these videos, right, you can identify these shots. Like shots means when you detect this transition of shots, and then when you prune your token, you should do it within the shots. Right? That way, it's easier to identify these redundancies, and for redundant, just remove. Right. So that's what we did, and then we have a better way to do this audio, video, like a joint prompt to improve, and then we get a better performance. Okay, and finally we found that the problem is still there is a lacking of a data set, right? So the last paper is that we try to build a large benchmark data set that is basically you can use like a GPT kind of a large model to look at this video data set and prepare the question for you. Right? So we prepare 3 kinds of questions, like an easier question, a yes, no, or harder question. You have to really understanding the spatial temporal reasoning and to answer this kind of question. But the thing is that the model still do not understand this. The model now is still work based on large train on larger data set, right? So then the question here is that we say that we make a data set that 10 times larger than all the others, right? And then we sort of apply the best model and sort of get a good result, right? So that's what's happening here. Okay, yeah, let me try to wrap up. I think, I have a lot of things to skip up. I'll move to this DGM ninja forensics, right? So this is like, so for the problem here is that given image, you want to find out where, it's the algorithm, right? So defect detection in this case. Okay, so then we sort of, but the interesting thing here is to design your method based on this periodical cues, right? So for example, right, in this picture, right, one of this is fake, right? So what we found out is this: if you look into the pupil, right, this pupil is not circle. So why is that? Because again, it goes to the data set problem. When it's again, right, generating adversarial network was trained, the loss function you constrain to generate this nice picture, they do not constrain, this thing has to be circular. Right, so that's why we use this queue, and then basically we just design a segmentation, like a model that can segment this pupil and then fit a boundary sensitive IOU, and then, you can do this kind of, you can separate these 2 cases. Right, this is like one example to show that, you can do defect detection that way. Okay, yeah, and we will do defect on the audio as well. This DAPA forensic, semantic forensic program that we work on for many years, and we have this, this image manipulation detection problem that is, again, it's like a data set again, right? So you can I mean, the problem is that I want to detect anything that's copy paste Photoshop, right? And then you can scrape this Photoshop and generate a lot of things you have run through, right? Because I put something in, so I know, right? So we want to detect this copy move, writing, and removal kind of editing by using like an HRNet kind of like a segmentation network. So basically, it's like you treat this forensic as a segmentation problem, and the segment the thing is that 0 for authentic, 1 for forgery. So and then there's a way to tune it and then improve to detect on this JPEG compression and etc. Okay, yeah, definitely for the time's sake, I cannot talk about all of these joint works, which are some of them are wonderful. I will move on to the wrap up. Okay, so yeah, I think for the research paper I talked about, you could review just like individual incidents under this big umbrella or big roadmap of this agentic and trustworthy AI. So like I said, right, so agentic AI is like the driving force, right, that you can use to automate a lot of things and bring you a lot of breakthrough. And it's continuing being better. Right, this agent is getting, I think, better, smarter, less and less hallucinations. You can address, and people are addressing it. Okay, so that's the driving force. And then the second point, the trustworthy AI, I think is a recursive model to tell you that, look, the agent is not like there yet to be like you can safely use it on your everyday life, right? So if you relax the problem set up or the constraints, then the best model out there is no longer best, right? So that's the trustworthy argument, right? For example, right, if your GPT is so good, when you try to run it on your edge, you have to run it, you have to like quantize and reduce by scale a lot, right? So then, that's the efficiency argument, right? So the trustworthy AI, I see, what I see is like a big umbrella that with many aspects and fronts that you can improve. Each of the fronts you want to improve is a research problem, okay? And the future, I would say, we are moving toward, combine these two, right? The agentic AI and the trustworthy into these world models. So eventually, hopefully, we will see some kind of robot that can move on its own and has a body and can do things as good as like a human beings. That's the roadmap. Okay.
Thank you very much.
Thanks, everyone.
This was really excellent. I want to take a few minutes extra, if you can stay on. So, our PDH requirement our IEEE has a requirement for PDH credits. Some people are attending for PDH credit. So there are 5 questions I'm going to ask, and anybody can answer. Let me just share my screen.
Should I like unshare?
Yeah, I can share. And it's very simple. These are simple questions. Okay, so can you see it?
Can I? So how do I do it?
You have to share this.
I can share.
So I will stop sharing.
I think it should work. Yeah.
Oh, okay, yeah. I have to share this. Okay.
How does it work?
It's fine.
Oh yeah, this is the question. What is the key characteristic of agentic AI? Sorry.